Hey there everyone, welcome to another quant reasoning video. This is Unit 8B, Chapter 8, Section B, doubling time and half-life. We talked about exponential growth and decay in the 8A video as part of our linear versus exponential information. This is a specific type of exponential growth and decay. The time required to double during exponential growth is called the doubling time. The time required to half or cut in half is called half-time. So if you go, the amount of time it takes an investment to go from $1,000 to $2,000 is the doubling time. The amount of time that it takes a radioactive isotope to decay from 1 kilogram to a half a kilogram, that's called the half-time. And that length of time can be determined during experimentation, or it can be determined through some modeling processes, and we're going to talk about some of those here in this video. Okay, so the time required to double is represented by this capital T, and sometimes we put a little T double there to specify, but if you have an amount of time little t and you are exponentially growing with a doubling time of big T, then your factor of increase is 2 raised to the t divided by big T power. So what we're doing is we're taking a ratio like this. Okay, so example, if big T was 10 years and we were investing for 5 years, then 5 out of 10 would be what? That would be 1/2, or 2 raised to the 1/2 power basically is going to be the amount you've done half of the work to double it. Now that doesn't mean you're 1/4 of the way there, because it doesn't work that way. It's exponential growth. Okay, but what that means is that t equals 5 years is half the required time to double it. And so that's why the power becomes 1/2. Okay, so let's do an example, make it a little bit more clear. Compound interest. Interest is just a thank you, a monetary thank you that a bank or a corporation gives you for letting them use your money. And so let's suppose your bank has a doubling time of 21 years. By what factor does your balance increase over 50 years? So the idea here is that we are going to take big T, which is what? Big T is 21 years. That's how long it takes to double. And the time that we're interested in is 50 years. So we're going to take 2 and we're going to raise that to the 50 divided by 21. That's our ratio, because the doubling time goes on the bottom. Okay, and so if you plug that into your calculator, you'll see that you get 2 to the 50 divided by 21, which is about 2.38. And so 2 raised to the 2.38 is 521. Okay, so this is 5.21. And what that means is that's the number of times that your amount will go up. So if you start with a balance of $1,000 in 50 years, it would be worth $5,210 because you multiplied 1,000 by the 5.21. That's what we call the factor of increase, or the growth factor. Okay? And so another way to think about that is to write it out as an exponential formula. So the exponential formula, remember ours from last section, was ab to the x power, where a is what? A is your initial amount. Okay, and b is the growth rate. Well, in this case, b is 2 because we're talking about doubling time. So what I want you to do, I want you to read through this problem. You can go back here if you need to, but I'm doing it in a slightly different way this time. I'm trying to get you to think about it as an exponential function from last section. Okay, so read through this problem, hit pause, try to do this problem on your own. If you get it, great. If you don't, no big deal. Okay, and then we'll talk about it in just a minute. So go ahead and hit pause, give it a shot. Okay, so what do we have here? We have A, our initial amount is $1,000. Doubling time is the big T, that's every 20 years, so big T is 20. And after 12 years, that's the time we're interested in, and so that's little t. So if we plug all these things into this formula here, we get y equals $1,000 times 2 raised to the 12 divided by 20. Remember, big T goes on the bottom. The amount of time we're interested in goes on the top. All right, and then we have to use our calculator. We're going to have to take 2 and raise it to the 12 over 20 power. So make sure that you use parentheses when necessary and put 12 divided by 20 up in the power parentheses. Okay, and so 2 raised to that power, if you plug that in your calculator, you get 1.5157 da. All right, and so if you multiply that by 1,000, then you'll get the amount of money rounded to the nearest whole dollar. We get 1,516, $1,516 rounded to the nearest whole number. Okay. All right, now the other thing that you can do on occasion with doubling time is if you're given the growth rate of an exponential increase and it's given as a percentage, then the doubling time can be approximated. It is an approximation with this formula, the rule of 70, 70 divided by P, where P is the percentage as a percent. So notice that P has the symbol with it. If you're talking about 7%, then P is actually 7 in this formula, not 0.07, but 7. All right, so as an example, the world population doubled in the 40 years between 1960 and 2000. What was the approximate average percent growth rate during that period, and then contrast it with the known growth rate of 2012. All right, so how's that going to look? All right, we take this formula, but we solve it for P. We had 70 over P is equal to T, and so what we did was we multiplied both sides by P and divided both sides by T, and we got this. Okay, and we could have plugged in and solved for it directly. It would have been fine to do that as well. All right, so anyway, what does that look like? If T double is 40 years, then when we plug that in, we end up with 70 divided by 40, which is about 1.75 per year, or 1.75% per year. That was the growth rate during that 40-year period from 1960 to 2000. Okay, how does that compare? Well, obviously that's a little bit more than the 1.1% per year that was happening in 2012. So the growth rate slowed down. I think we've known that for a little while. And so there you go. That's the way you use the doubling time approximation. And I will tell you whether to use the rule of 70 or to figure it straight out. Okay, don't use the rule of 70 unless I tell you to. Okay? All right, so going the other direction. Going the other direction with half-life is exactly the same formula as before, except now we have a 1/2 instead of a 2. We still do the little t over the big T, where big T is the half-life, okay, and little t is the time that we're interested in. But we can use this formula, or we can just look at the decay factor, 1/2 raised to the power, like we did before, okay. So in this problem here, radioactive carbon-14 has a half-life of 5,700 years. That's big T, right? And it collects in organisms only when it's alive, and so once you're dead, then it decays, and that's why we can measure how old something is using carbon-14 dating. Okay, it really only works for things that are a few thousand years old, not for things that are, millions and millions of years old. But whatever. And so what fraction of the carbon-14 in an animal bone remains after 1,000 years? So that's my little t. That's my little t. So little t is 1,000, big T is 5,700. What we do is we do this 1/2 little t over big T. What does that look like? It looks like 1,000 divided by 5,700. So if you type that in your calculator, 1/2 in parentheses and then raised to this power, and again, depending on your calculator, you'll need parentheses here too, and you get 0.885. Okay, so that's the ratio of the original amount compared to how much it had now. And so, for example, if a bone originally contained 1 kilogram of carbon-14, then how much after 1,000 years would be about 0.885 kilograms. So a little bit less than 0.9 or 9/10 of a kilogram. So you can see that it decays very slowly. Okay. So let's do a problem. You guys do this problem. The half-life of plutonium-239 is approximately 24,000 years. So that's given right here. Okay, significant length of time. Radioactive isotope. And let's suppose we started with 100 pounds. How much of it is still around 100,000 years from now? Obviously, that's the little t, right? So again, what we're doing is we're doing our formula from before. Y equals, that's the new value, equals A 1/2 t to the little t. All right, so y'all plug in that formula, pause the video, and see what you can get. Okay, so when we plug that into our calculator, again, be real careful when you're doing your calculator. You're going to get 100 pounds times 1/2 with 100,000 divided by 24,000. Okay, and again, you may need parentheses around these two guys depending on your calculator. And if you plug all that in at one time, you should be able to hit enter and get 5.6 pounds. Make sure you label it properly with units when units are appropriate. Okay. All right. Finally, just like doubling time, the half-life formula has an approximate half-life formula. It works best for small percentages, and P is the same way. If P is given as a percentage, if it's 8%, then 8 goes in for the P. All right. So as an example here, suppose inflation causes the value of the Russian ruble to fall at a rate of 12% per year relative to the dollar. All right, at this rate, how long does it take for the ruble to lose half its value? So we're approximating it using T over 70, using T equals 70 over P, approximately anyway. And so we plug in 12, 12% means P equals 12 per year. And so dividing by per year means you're actually multiplying and going to get a year out of here. And so 70 divided by 12 is 5.8, round to the nearest tenth, or round to the nearest whole number is 6 years. Okay? So as always, work the MyMathLabs. Let me know if you have any questions, and check out the worksheets in D2L. And we'll see you later. Thanks.